a branch of mathematics that has existed for about 35 years that focuses on this question of, well, if you have some number of computers, then how do you get them to kind of quickly agree on data, even if some of those computers have been hacked or go offline or something happens to them. And now, that kind of consensus was originally designed in the context of a setting where you know ahead of time that these are the 15 people participating, and so you just give one of them a kind of participation token and everyone knows who all the participants are.
Yes.
And that's why you can't just directly transplant that into a open public network setting, and that's why Satoshi went over to proof of work initially. But our idea is to take those algorithms and, first of all, kind of merge them together with proof of stake. And second, we came up with an algorithm that has some intermediate properties between the properties of these older BFT algorithms and chain-based proof of stake. So the problem with the older BFT algorithms is that they're designed for like 15 computers, and so if you try to run them with 50,000 computers, you need like extremely powerful computers that you basically, the only people who would run nodes are like Google. So in our case, we have a version of this algorithm that takes longer to come to kind of final consensus, but still not too long. And even before it comes to final consensus, it kind of interweaves this BFT style of consensus together with a kind of chain-based style of consensus, but also not, kind of not chain-based. And the benefit that this gives you is that within something like 5 seconds, you get a sort of soft agreement that this block is probably part of the history forever. And then in a couple of minutes, that soft agreement upgrades to a final finality and it's not going back.
Interesting. If any of you are familiar with the world of payments, with Visa, you get auths and settlement, right? When you go to make a payment, the thing that happens when you go to pay with your card is Visa says, oh yes, there's money in this account. The money doesn't actually move till a day later. That's actually similar, but what you're saying is it's happening on a much more compressed time frame for that network. Interesting idea. All right, Colin, any further follow-ups on that point?
Follow up on that.
Yeah.
So one of the things that I thought was really interesting in discussion that I've heard over the last couple of months in the Ethereum community is a notion of economic abstraction. So being able to use multiple different kinds of coins or assets to pay fees rather than having to go through only Ether. Can that exist in a proof of stake or in a Casper type setup?
So proof of stake does inherently require there to be one enshrined or privileged currency in the network, because you need to have one currency that the proof of stake deposits are in.
Right.
And there are reasons why in some cases you might want to enshrine one particular cryptocurrency further. So one example of this is that there are benefits in some cases to having a model of transaction fees where instead of the miner deciding what to accept and you deciding how much to pay, there's some fixed fee that might be adjusted by some mechanism, but it's a fee that the protocol chooses and where the coins actually just get eaten up by the protocol. And if you want to do things like that, you need to have one particular currency that those fees are denominated in. That said, we definitely recognize the usefulness of economic abstraction as a thing that is good for usability and good for making applications more accessible and so forth. But I think there are many ways to achieve this goal. So more recently, we've been kind of bigger and bigger fans of this kind of layer 2 approach to design, where we make the base layer of a blockchain both reasonably simple, but also maximally general, so that if you want to build these more specific features on top, you can build them like basically as software libraries or systems of smart contracts that just sit on top of the blockchain.
Interesting. So that second layer gives you the space to be able to kind of do all of those abstractions in a completely different way, whilst the general layer underneath that's doing the kind of the general stuff.
Exactly.
It makes a lot of sense to me, and it kind of hints at those layer 2 things that we've been talking about historically. Those technologies, Plasma and Raiden are often brought up as potentials in that space, and we also get into sharding. Just walk me through what those technologies are and where they fit within that stack.
Sure. So sharding is a base layer upgrade. So it's an upgrade to the blockchain itself.
Yes, it's
and what sharding does is it changes the structure of the blockchain so that instead of every single computer in the network needing to download and verify literally all of the data that anyone sends, you break up the data into shards, so basically pieces, and some small random selection of nodes verify each individual piece of data. And the purpose of this is essentially that it allows you to still have the whole chain be verified, but at the same time do not require any individual node to process more than, maybe 1/500th of the entire data that's being processed by the chain. And so you increase the scalability of the entire system by a factor of maybe something like 500.
But is there a trade-off there in terms of the overall security, or is that, where is that trade-off?
There definitely are trade-offs, but the good news is that there's not any kind of trade-off that says security goes down by a factor of 500.
Right.
Like, there are more naive designs that people have thought of before where it actually is the case that if each node only needs to process 1/500 of the data, that means that if you break 1/500 of the network, you can break one of the chains. But the more recent designs use multiple layers of defense. Like one of them is a random sampling mechanism that basically means that if you are an attacker, you don't know ahead of time which nodes will have to verify what data, so you don't know which nodes to take over or attack or become in order to attack a particular part of the chain.
I see.
There's also something called data availability proofs, fraud proofs, proofs of custody. So these different strategies together that actually do mean that the amount of security that you're losing from this design still exists, in large part just because it is a significant gain in complexity, but is definitely not a kind of massive decrease in security that'll make the chain vulnerable.
Are you guys testing that, I guess, on a test net, and what have you seen in terms of the gains and some of those trade-offs? Because, I mean, until this is put out to the public, a lot of it is unknown, right? I mean, you guys learn so much every time you do a release with Frontier, you suddenly see all of the things you didn't think of. Is that a concern going into?
A lot of this stuff is definitely still theoretical, so the test nets are fairly far along in development, but so far the testing has focused much more on the proof of stake side than the scalability side. And our intention is to release the proof of stake part before the sharding part, because we want to have a period which is kind of like an early test where the chain is theoretically running, and you get to test to make sure that the proof of stake parts are all actually working.
Sure.
But also at the same time, it's kind of a real live economic test where the economics of proof of stake are being tested because it's people's actual deposits and money are at stake.
Well, so then you're just testing that. You're not testing that plus sharding and introducing additional risk.
So the point is that we would launch the proof of stake part first, and because with the proof of stake part, there's not going to be much activity connected to the chain. It's not even that bad if it breaks, and so we can afford to do more testing earlier, and then when things stabilize a little more, we'll push sharding out. And, we'll continue actually implementing and testing the sharding itself in parallel to all of that.
Indeed, that makes complete sense.
Sharding is definitely a challenge in implementation in multiple ways. I think one of the big ones is that you do need to use fairly novel kinds of peer-to-peer networks, because the peer-to-peer networks used in Bitcoin, Ethereum, basically every blockchain and cryptocurrency so far tend to be gossip networks, so they rely on this assumption that every node broadcasts something that everyone downloads, but that's just fundamentally incompatible with the sharding approach to scalability, and so there's a kind of go back to square one moment. Though it is something that our peer-to-peer network researchers are fairly far along in figuring out the solution we're going to use.
But it's going to be an interesting challenge for sure. Colin, any follow-ups on this one?
Yeah, so it's kind of a general question on security, be it sharding proof of stake or proof of work as it exists. In your opinion, is there kind of a maximum required amount of security, if we call it level X, that going beyond it really just never makes any sense? Or do you think it's a sliding scale?
There is definitely a sliding scale. There are specific points on the scale that are worth highlighting. So for example, if the number of nodes that on average validate a particular piece of data drops below somewhere between 100 and 200, then you get a risk that an attacker with a relatively small share of the network will be able to just corrupt specific pieces of data by random chance.
Yeah, okay, yeah.
There's also the risk that if a particular piece of data is stored by only a few hundred nodes, then it will happen that at some point there's one piece of data that literally everyone forgets and then it's unrecoverable. So there's definitely, in my opinion, a natural kind of floor to the extent to which we can get the inefficiencies down, at least at base layer.
Yeah.
And somewhere between a factor of 100 and a factor of a few thousand seems to be where that floor is.
Interesting. So, and then on the top end, is there an alternative to that? Is there a side at which it becomes so inefficient, or is actually the idea is that it has to be a world computer?
This is called Bitcoin and Ethereum 1.0
Yes.
and all these other systems that exist today.
So yeah, that's fair. So then, speaking of the kind of the base layer and then moving up to layer 2, there's a couple of layer 2 technologies out there. Of course, Bitcoin has its own with the Lightning Network, and there are a lot of different discussions about the pros and cons of layer 2s. So let's define layer 2, talk about pros and cons of the concept of layer 2 solutions, and then talk about the Ethereum specific ones.
Sure. So the general idea behind layer 2s is that instead of trying to scale the blockchain itself, you change the way that applications that use the blockchain are designed so that instead of shoving literally every single interaction between an application's users onto the blockchain, they try to make interactions happen between users directly first, and then only push data to the blockchain in the event that there is either a dispute or some kind of failure on the part of one of the participants, or you want to exit the system and possibly switch to a different layer 2. So the simplest mechanism to explain is probably payment channels, and we could even go through payment channels. That's a fairly illustrative example. So let's suppose, for example, that I'm trying to sell you an internet connection.
Yep.
So I have a phone, it's connected to some cellular network. You have a phone, it's connected to nothing. You want to borrow my data at the cost of 4 cents a megabyte. Then we connect to each other. You put, let's say, $5 into a channel. And then a channel is a smart contract, so you put the $5 in, and by default, you have the right to just take the $5 out at some point later at any time. Now, then if you want to pay me for 1 megabyte, so I do 1 megabyte of data, instead of you publishing a transaction on-chain, you sign a ticket. So you sign a message off-chain that basically says, all right, I agree that I have now given up 4 cents, signed Simon. And you send this to me, and now I have it. Now, if you want to pay for another megabyte, then you sign another message, and the second message says, I now agree that I have been willing to give up 8 cents. And then you sign a third message that says, I'm now willing to give up 12 cents.
Yes.
And the rules of the smart contract say that either of us can start and exit from a channel, and then after that, there is some period of time during which either of us has the ability to submit messages, and the message that has the highest sequence number attached, so basically the message that is the latest, is the message that wins. And so if I have a ticket that says I received $2 from you, then I myself know that within this period of time within which either of us can send messages, I can send the $2 into a channel, and I know I'll be able to get the $2. And so the clever trick that's being done here from an economic perspective is that even though the base layer itself is not being modified every time we send a message, but the base layer implements this kind of game